How to completely graph a rational function without really trying. The epic final conclusion to the introduction of rational functions. Part 1. Previously on Algebra 2.
Jean-Luc.
We were not supposed to leave.
Jerry Ying here. Hello?
So a point of discontinuity is basically anywhere that would make the denominator a 0. It's an x value that would make the denominator 0. And so to find that point, what we do is we take our denominator and we set it as equal to 0 and solve.
I am Locutus of Borg. Resistance is futile.
We have to go back, Kate.
Now there are actually two types of discontinuities. One, we have the removable discontinuity, or a hole, and that's whenever we have a factor that would cancel out, like the x plus 2 on this slide. The second type is a vertical asymptote, and that is a factor in the denominator, like x minus 1, that doesn't factor out. But Mr. Peacock, you may be asking, what about x minus 3? Well, that's not a discontinuity. That's a root. And a root is where the function crosses the x-axis. In order to get a root, the numerator is set to 0 after the function is simplified.
We have to go back!
Mr. Worf. Fire.
We've learned about vertical asymptotes, but what about horizontal ones? Find out on today's Algebra 2. Horizontal asymptotes have a different set of rules.
Almost. There are a few provisos, a couple of quid pro quos. Like? Rule number 1.
If the degree of the denominator is greater than the degree of the numerator, that means there's a horizontal asymptote at y equals 0. So here's an example. If you look right here, the degree of the denominator is 2, where the degree of the numerator is just 1. That means denominator is greater than 0. So the horizontal asymptote would be y equals 0. And we have a rule for that, and it's called BOBO. BOBO means bigger on bottom 0. And that is for when y equals 0.
Rule number 2.
If the degree of the numerator is larger than the denominator, then that means that there is no horizontal asymptote. So that would be like this. If you look right here, third degree compared to second degree, the bigger one's on top. So we use BOTN. Bigger on top, none. And in that case, there is no horizontal asymptote.
Rule number 3.
If the degrees are the same, that means there's a horizontal asymptote at the ratio of the leading coefficients. So if you look right here, our degrees are both squared. So as time goes on, that minus 4 isn't really going to affect much, so it just becomes 2 over 1. So our rule is eats DC. And that means exponents are the same. Divide coefficients. So exponents are the same, divide coefficients, meaning in this case 2 over 1 or just 2. So just remember, BOB0 BOTN eats DC.
Hi, I'm BOB0 BOTN. Yummy.
All right, let's find the horizontal asymptote in this case. So if I look right here, I'm looking at my degree, and they are both the same. So if I'm thinking about my rules, that's like eats DC. Exponents are the same, divide coefficients. So my top coefficient is -2. My bottom is 1, meaning y equals -2. All right, let's try another one. In this case, if you look, my top degree is 2, my bottom degree is 1. That means bigger on top, none. All right, let's look at our third one. So in this case, even though we can't see it, this is really x times x, or x squared. So that means bigger on bottom, which means y equals 0. Bobo. All right, so now that we have all that information, when we put all that information, removable discontinuities, vertical asymptotes, horizontal asymptotes, roots, together, we can get a good idea of what the graph of a rational function looks like. So let's look at this one, and we're going to sketch a graph. So the first thing I would want to do in this case is I would want to factor out. So in this case, let's see, I have two numbers multiply to be 1, add up to be 2. That means x plus 1 squared, or as I'm going to write it, x plus 1 over times x plus 1. So if you look right here, those cancel out, leaving us just x plus 1. So that means our final graph is going to look something like, let's move that up just a little. There, that looks better. But there's going to actually be a removable discontinuity. So the removable discontinuity is going to be at, let's see, if it's x plus 1, that's going to be at -1. So right there at one of our zeros, which is also where a root would have been, except for the fact that there's a discontinuity there. Let's try another one. 4x over 4x squared minus 8x. So that would simplify to be 4x times x minus 2, meaning our final version after these cancel out would be 1 over x minus 2. So I know that there is a vertical asymptote at my 0 on the bottom, which is at 2. So let's change that color. So I know that there is a vertical asymptote there, and that my graph will basically just look like that. Now the only thing that I have to deal with here is my other point, which is my removable discontinuity. And so 4x equals 0, that means x equals 0 right there. All right, let's try this one. And right here, if you look, these look the same. That means my final graph is just going to look like, well, 1 over 1, or just right there. Now, I do have to find my zeros, so let's see, two numbers that multiply to be 12 and add up to be -1, that's x minus 4, times x minus 3, x plus 3, so let's see, -3 is one of my zeros, and then +4, but because those are on top and bottom, those are just removable discontinuities. And so that's what our final graph would look like. And that's it for today. Thank you very much. Have a good day. Please be sure to like and subscribe.